Hey there, and welcome. Today, we're going to unlock some of the secrets behind our modern digital world. We're diving into how a simple, shared key can be the one thing that protects our most valuable information. Come on, of course you have. We all have. Whether it was a folded up note in class or just a private DM, the goal is always the same, right? You want to make sure only the person it's for can actually read it. And you know what? That simple idea is the absolute heart of modern cryptography. So here's our game plan. We're going to start with the one big rule of this whole system. Then we'll see how regular messages get transformed into secret ones. After that, we'll look at the simplest way to do this, a method called the electronic codebook. But then we're going to expose a huge weakness in that method and show you the really clever fix that makes our data so much safer. All right, first things first. Before we get into any of the cool, complex stuff, we have to establish the single most important rule in this entire system, and it's all about using just one key. This whole idea is called symmetric key cryptography. And honestly, the best way to think about it is like a special lockbox. You've got one single unique key. You use that key to lock the box. Then you send the box to your friend, and they need an identical copy of that exact same key to open it. One key does both jobs, locking and unlocking. And this diagram here shows that process perfectly. You've got Ali on the left. He takes his message, we call that the plain text, and he uses the shared key to encrypt it, to scramble it up. That jumbled message can now travel over any open channel, it doesn't matter. When Booty gets it, he just uses his identical copy of the key to decrypt it and get the original message back. Simple. But wait, this brings up the most important question of all. How did Ali and Booty get the same key to begin with? Well, they had to share it over a secure channel, because if anyone else gets their hands on that key, the whole system is totally broken. So we have our key. We know it's a secret. But how does it actually transform a message you can read into one that you can't? At its most basic level, it's actually pretty straightforward. You take a chunk of your message, the plain text P, and you feed it into an encryption function, E. That function uses your secret key K to do its magic, and what comes out the other side is a block of ciphertext C. That's your scrambled message. To turn it back, the person on the other end just runs that ciphertext through a decryption function using the very same key. Now, in the real world, we don't usually encrypt a whole long email or a big file all in one go. That would be pretty clunky and inefficient. Instead, modern encryption systems break the message down into smaller, much more manageable pieces. And this method is called a block cipher. So let's go back to our analogy. Instead of one giant lockbox for your whole letter, imagine you wrote your message on a stack of small, identical note cards. Each one of those note cards is a block, and each block gets locked away in its own tiny little box, one at a time. Okay, so there are different strategies, or modes, for encrypting all these blocks. Let's start with the most direct, the most straightforward one of them all, the electronic codebook, or ECB. The rule for ECB is dead simple. Every block for itself. Each piece of plain text gets encrypted completely on its own, totally independent of what happened to the block before it or what's going to happen to the block after it. It's kind of like an assembly line where each station just takes one note card, locks it in a box, and sends it down the line without ever paying attention to the other stations. And you can see that independence perfectly in this diagram. Look at how each plain text block goes through the encryption process with the key, totally separate from its neighbors. You could theoretically encrypt all of these blocks at the exact same time. They have absolutely zero influence on one another. All right, theory is great and all, but seeing this in action makes it so much clearer. Let's actually encrypt a quick message using this ECB mode. We're going to keep things really simple. We'll start with our message, just a string of ones and zeros. Then we'll chop it up into small, equal-sized blocks. We'll pick a secret key, and then we'll apply a simple encryption algorithm to every single block. Okay, so the first step here is to combine each plain text block with our secret key. You can see our key, 1011, is being applied to every single block in the exact same way. But pay close attention here. Do you see the first block of our message and the fourth block? They're identical, 1010. Keep that in mind. It's going to be really important in a minute. And boom. After the final step in our algorithm, we have our ciphertext. Our original message is now a jumbled mess of numbers, completely unreadable to anyone who doesn't have the key. Looks pretty good, right? I mean, it's secure. Or is it?
Turns out there's a huge problem hiding in plain sight. This simple and kind of elegant method, it has a really critical structural flaw.
I mean, you're probably thinking, what's the big deal? The message is scrambled. And you're right, it is. So what's the problem here? This is it. This is the Achilles heel of ECP mode. Remember in our example how we had two identical plaintext blocks, that 1010? Well, because every block is encrypted independently, using the exact same key, they produced identical ciphertext blocks. And that creates patterns. An attacker might not know what the block says, but they'll know it's a repeating piece of information. And believe me, in cryptography, patterns are a gift to the bad guys. It gives them a huge piece of the puzzle.
So how do we fix this? We have to find a way to break those patterns. We need to make sure that even if we encrypt the exact same block 100 times, it looks different every single time. And the way we do that is by creating a chain reaction. The solution is called cipher block chaining, or CBC, and it is seriously clever. Here's how it works. Before any block of plain text gets encrypted, it's first mixed together with the ciphertext of the block that came right before it. This means the result of encrypting block 1 directly influences how block 2 gets encrypted, which influences block 3, and so on and so on. It creates a chain. So now, even if you have two identical plaintext blocks, like our 1010 from before, they will produce completely different ciphertext. Why? Because the encrypted block that came before them was different. Just like that, the pattern is destroyed. And this evolution, right here, from a simple but flawed codebook to this clever, interconnected chain, is absolutely fundamental to digital security. It really makes you stop and think, doesn't it? How much of our online banking, our private messages, pretty much our entire digital lives, depends on getting these tiny, intricate chains exactly right.